In this video, we're going to look at the normal and binormal vectors. Previously in this section, we looked at capital T of t, which was the unit tangent vector. That was defined as being r prime of t divided by the magnitude of r prime of t. If you have a 2D function, the tangent gives you the slope of the function at a given point. If you have a curve in 3D, the tangent is going to be a little bit more complicated. So one way we can describe a tangent is by using the unit tangent vector. That's basically just describing where your curve is headed at any given value of t. The normal vector and the binormal vector are two other vectors that are also useful for describing the path of the curve. The normal vector is denoted as capital N of t, and this is just equal to t prime of t divided by the magnitude of t prime of t. Notice this is really similar to the equation of t of t. For t of t, we just took the derivative of the function and divided by the magnitude of that derivative. If t of t described how r of t was changing at a given point, the normal tangent vector is describing how t of t is changing at a given point. And then the binormal vector, denoted as a capital B of t, this is just the cross product of the unit tangent vector and the normal vector. Let's say we define a vector value function with the x component as sine of 3x, the y component is cosine of 3x, and the z component is sine of x. In Geogebra, we can create a curve based upon this input using the curve function and then putting f of t, g of t, h of t as the equations for the x, y, and z components. We can define d of x as being the magnitude of r prime of t, and then curve B would be our unit tangent vector. The unit tangent vector just describes where is the curve headed at any point of t. We can then find W, which is the normal vector, and that's going to end up being perpendicular to our tangent vector. So what you're seeing in red here is the tangent vector, and then in green, that is the normal vector. The binormal vector ends up being orthogonal to both the tangent vector and the normal vector. So here's an example of how to find the tangent vector, the normal vector, and the binormal vector. We're going to do this for both problems A and B. Let's jot down the equations we have to use. T of t is equal to r prime of t over the magnitude of r prime of t. That's the unit tangent vector. The normal vector is t prime of t over the magnitude of t prime of t. And then the binormal vector is t of t crossed with n of t. First we have to find the derivative of r. I'm going to write this in component form, and r prime is just negative 4 sine of t, and then negative 4 cosine of t. Next we need to find the magnitude of that. That's just going to be the square root of the x component squared and the y component squared. If we factor out a 16, we get sine squared plus cosine squared, which would be 1. That leaves us with the square root of 16, which is 4. So then the unit tangent vector would be r prime of t divided by the magnitude of r prime of t, which ends up being negative sine of t, comma, negative cosine of t. Now let's work on finding the normal vector. We first have to take the derivative of t. That would be negative cosine of t, comma, sine of t. Then we need to find the magnitude of that, which ends up just being equal to 1. Our normal vector is just then going to be negative cosine of t, comma, sine of t. Since our vector value function is just two-dimensional, that means that there will not be a binormal vector for this. You can only have a binormal vector if you're dealing with a 3D curve. Now for part B. This one's going to be pretty tricky. R of t is equal to 6t plus 2y plus 5t squared j minus 8t k. We start by finding the derivative of r. That would give us 6 as the x component, 10t as the y component, and negative 8 as the z component. For the magnitude of that, we square each of those components, add them together, and take the square root. We can add the 36 and 64 to get 100. That would give us the square root of 100t squared plus 100. If we factor out 100, we can then move that outside of the radical by taking the square root. That would give us 10 times radical t squared plus 1. At every step along the way, you want to simplify things just as much as you possibly can for these problems. Otherwise, things just get completely out of hand. Now we can find t of t by dividing those last two answers. T of t is going to be r prime of t divided by its magnitude. We can divide the x, y, and z components separately by that 10 radical t squared plus 1. That would reduce to 3 over 5 radical t squared plus 1, t over square root of t squared plus 1, and 4 over 5 square root of t squared plus 1. Next up is t prime of t. We have to take the derivative of each of those components one at a time. We're going to have to use chain rule for all three components, and then that middle one is quotient rule as well. Let's do some work on that middle one to try to simplify it as much as we can. At the very beginning, notice the 2 would cancel with the 1/2, and then what's left is the square root of t squared plus 1 minus t squared over the square root of t squared plus 1 all over t squared plus 1. I went ahead and split this into two different fractions, and then for the right fraction, I'd combine that radical with the overall denominator of t squared plus 1. That gave me t squared plus 1 raised to the 3/2 for that denominator. To find a common denominator, I then had to multiply that left fraction with the square root of t squared plus 1 over the square root of t squared plus 1. Now that we have a common denominator, we can combine these two fractions, and then the t squared cancels with the negative t squared. That then simplifies to just 1 over t squared plus 1 raised to the 3/2. So then this is what t prime of t looks like fully simplified. Notice I did change the y component just so that the x, y, and z components all have the same denominator. That'll help us out in a minute. Now that we have t prime, we can work on finding its magnitude. That would be the square root of the x, y, and z components all squared and added together. Since we have a common denominator, we can square everything and then put it together as one big fraction. After combining like terms in the numerator and then factoring out a 25, those 25s will cancel, and then also that t squared plus 1 in the numerator cancels with one of the t squared plus 1s in the denominator. So then that simplifies to the square root of 1 over t squared plus 1 squared, and if we take the square root of that, we just get 1 over t squared plus 1. Now we can find the normal vector by dividing t prime by its magnitude. So here's t prime, here's its magnitude. Since we're dividing by a fraction, you can just use keep, flip, change, and then the normal vector just simplifies to this. Now here comes the fun part, finding the binormal vector. We have to take the cross product of t and n. To find a cross product, just create a matrix. The first row is ijk, the second row is t of t, and the third row is n of t. This is one ugly looking matrix. We have not found the cross product of anything quite this complicated yet, but it's still doable. Just remember the steps. First, you want to cover up this first column, the I column. You want to multiply this diagonal and subtract it with this diagonal multiplied. All of the denominators are the same, which means when we multiply all these fractions, we're always going to end up with one of those denominators squared. So then the coefficient of I ends up being 20t squared plus 20 all over 5 squared times t squared plus 1. Then cover up the j column and multiply the top left and the bottom right, and then subtract it with the top right times the bottom left. You want to make sure that you're subtracting this term. And then the coefficient of j becomes negative 12t minus 12t all over 25 times t squared plus 1. Finally, cover up the k column, multiply this diagonal minus this diagonal multiplied. That would give us 15 plus 15t squared all over 25 times t squared plus 1 times k. Now we just want to simplify. We can factor out a 20 in the numerator of that first fraction, and that would reduce with the denominator. That would leave us with 4 times t squared plus 1 over 5 times t squared plus 1 I. For the j, the numerator just ends up being a 0, so the coefficient for j is just 0. And then for the k, factor out a 15, and then the 5 inside of that 15 cancels with a 5 inside of the 25. We can further reduce this. T squared plus 1 over t squared plus 1, those cancel out. T squared plus 1 over t squared plus 1, those cancel out. So the final reduced answer for this would be 4/5 I plus 0j plus 3/5 k. We can model this inside of Geogebra just by going in and changing the f of x, g of x, and h of x of the Geogebra program that we used earlier. Set f of x equal to 6x plus 2, g of x would be equal to 5x squared, and h of x is equal to negative 8x. So there's the tangent vector, just showing you where the curve is headed at different values of t. There's the normal vector, which is telling you which direction the tangent vector is headed. And then there's the binormal vector, which is orthogonal to your unit tangent vector and the normal vector. Notice that Geogebra tells us that that binormal vector is 4, 0, 3. That's not actually the same as what we calculated. Why is that? If you turn on the axes, you can actually see that we're actually zoomed out quite a bit. If I had animated these as real unit vectors, you wouldn't have been able to easily see each of those vectors. In order to make them visible, I multiplied by 5 in front of the unit vector for the unit tangent vector. Let's see what happens if I undo that. I'm just going to delete that 5, and now that red unit tangent vector is a lot shorter than what it was. I also need to delete the 5 that's in front of the unit tangent vector for the normal vector. And then I compensated for me having to multiply times 5 inside of the binormal vector. So I'm going to delete that denominator here. Now if we animate this, we can see the unit tangent vectors to scale. And now if we scroll down and look at the binormal vector, it says that the binormal vector is equal to 0.8, 0, and 0.6. And 0.8, 0, and 0.6 is exactly what we calculated for the binomial vector.